In high-altitude flights, in industrial processes, in laboratory experiments, we often encounter gases that have densities thousands or millions of times lower than that of our atmosphere at sea level.
When the density of a gas gets less, the distance molecules of the gas can travel between collisions with one another increases. For example, at sea level, the mean free path of molecules of atmospheric gases is about 7 millionths of a centimeter, while at an altitude of 100 miles, the mean free path has grown to about 80 meters.
In this film, we'll watch some gas flows in which the mean free path is being varied widely. We'll see that flows in which the mean free path is very long, compared to our models or our vacuum chambers, look very different from those in which the mean free path is comparatively short.
We will look first at an extremely rarefied gas flow with the help of this molecular beam apparatus when it's assembled. We will produce our molecular beam by vaporizing sodium metal in a vacuum. Sodium will be evaporated in this small oven. The sodium molecules will come out here. We will look through these windows. In here is a second orifice. Some of the molecules will travel directly toward this second orifice and pass through to form a fairly well collimated molecular beam in the chamber above. We have pumped down to a residual gas pressure of about 10 to the minus 5 millimeters of mercury with our diffusion pumps. The flow will be illuminated by a sheet of light from this sodium vapor lamp. We'll take a picture of the flow from the oven first. What you are seeing in this picture is sodium light absorbed and then re-emitted from millions of sodium molecules coming from the oven into the vacuum chamber. The light intensity is proportional to the number of illuminated sodium molecules. When the molecules emerge from the oven, they follow straight line trajectories away from the oven aperture. At these low pressures, a negligible number of the sodium atoms make collisions with other atoms, either near the oven aperture or far away. We have free molecule flow. Since the paths are diverging, the density diminishes as the distance increases, so that we have to make much longer photographic exposures to make visible molecules reaching the upper chamber. Now let's look at those molecules coming out of the upper hole into the upper chamber. See how very sharp the edges of the beam are. This shows that molecules do indeed travel on straight lines between collisions. The flow is ray-like. We admit argon gas into the upper chamber to see what that does to the sodium beam. We now have a measurable pressure of argon, but one so small that the mean free path of the sodium molecules is still greater than the length of the beam chamber, and the picture looks just the same as before. The argon is invisible in sodium light. But as we continue to add argon, we see that the sodium beam fades out at the top. the increasing argon density decreases the mean free path of the sodium beam molecules, and hence reduces the visible penetration of the beam into the scattering chamber. The beam gets shorter and shorter. Now it's gone completely. In this rerun, notice that collisions with the argon don't cause the visible sodium light to spread out or to get fuzzy. This is because the scattered sodium atoms are dispersed into a very tenuous three-dimensional cloud, only a thin slice of which is illuminated by the sodium light. Some sodium molecules, of course, still travel to the top of the beam chamber even when the beam has been foreshortened out of sight. But they follow erratic and often interrupted paths. Actually, the kind of flow we find depends not just on the mean free path, but on the ratio of the mean free path to a characteristic dimension of the region of interest. In this case, the length of the beam chamber. This important dimensionless parameter is called the Knudsen number. This flow, with Knudsen equal 1, is right in the middle of the transition from this extreme to this.
When a space vehicle re-enters the atmosphere, it goes from free molecule flow with high Knudsen numbers to continuum flow with low Knudsen numbers as it descends through regions of continuously decreasing mean free path. The pictures we just saw were taken in this little wind tunnel, again using the sodium vapor flow visualization technique. A nearly constant flow of sodium is generated in the boiler here and mixed with a controllable flow rate of argon. The mixture then discharges through this converging nozzle and into the test chamber. The re-entry body of our picture is this little washer. It's electrically heated so that the sodium won't condense and collect on it. Right above the washer, we've placed the slit which defines the beam of sodium light. We control the test chamber pressure with vacuum pumps downstream, flow under free molecular conditions. We'll use a horizontal line to show the length of the mean free path of molecules approaching the washer. For this flow, it's rather long. Here's the Knudsen number. The characteristic dimension, d, in this case is the diameter of the washer. The washer casts a sharp aerodynamic shadow. This dark line is only the optical shadow of the washer. Sodium light comes in only from above. The molecules from the nozzle, which are intercepted by the model, are scattered back upstream. The purpose of the hole in the washer is to show what happens to the incoming molecules as they encounter the molecules scattered back from the model. The hole is so small, it has very little effect on the distribution of molecules in the backscattered cloud. We see that in free molecular flow, the cloud of backscattered molecules is easily penetrated, and the molecules approaching from upstream pass right through the hole to form a molecular beam behind the model. Now we'll admit more argon and thereby decrease the Knudsen number. Here you see the first departures from free molecular flow. Some of the incoming molecules have been scattered by collisions with the re-emitted molecules. They may still pass through the hole, but along trajectories which soon carry them out of the collimated beam and into a cloud too diffuse to be seen. What you see behind the washer is the reduced density of molecules which survive the trip through the re-emitted molecules without collision. Measurable deviations from the drag or heat transfer predictions of free molecule flow theory probably set in about now. As the mean free path gets still smaller, very few incoming molecules fly directly through this denser layer, and the collimated beam behind the hole has faded out. As the mean free path becomes small compared to the thickness of the compressed layer in front of the washer, the layer looks more uniform in density, and its upstream edge becomes more sharply defined. We recognize this edge as a slightly fuzzy bow shock wave of a blunt body in hypersonic flow. The fuzziness of this shock disappears just about as the mean free path line shortens to a dot. Now we are seeing continuum flow. The Mach number at the model location is about 9. Further decrease in the mean free path would make little noticeable change except in the wake behind the model. Let's look at that again. Now we'll look at a continuum flow from the same nozzle, but without the model. This flow has its own well-defined system of shock waves. The barrel shock and the Mach disk. We see a somewhat similar pattern of shock waves in the exhaust of rockets. These shock patterns are only clearly defined when the mean free path in the background gas is small compared to a characteristic length like the distance from the nozzle to the Mach disk. Under these conditions, the shock configuration depends only on the pressure ratio across the nozzle. We shall hold this pressure ratio constant at 100 to 1 and look at the result of increasing the mean free path by decreasing the argon flow. Let's look at that again. Now the mean free path is no longer negligible compared to the jet dimensions, and the shocks have become very thick and fuzzy. The barrel shocks have spread out until they overlap and are mixed in with the Mach disk. Now only this hazy, slightly bright spot remains to remind us of the shock system. And now, even that is gone. The jet molecules no longer collide with the background molecules, but fly straight past them to the chamber walls. The background molecules, for their part, can fly right through the jet without being hit. We have reached the free molecule limit, where the Knudsen number is large, and we see again that it is very different from the continuum limit.
In free molecule flow, the nature of collisions between gas molecules and solid surfaces and the resulting reflections are very important. For example, for bodies such as our washer, we need to state how gas molecules are re-emitted after they hit a solid wall when we calculate the aerodynamic forces or heat transfer. We can use molecular beams to learn something of how molecules scatter from surfaces. Here's a little surface. It's made of polished aluminum oxide, and we can control its temperature. We'll mount it in the upper chamber of our vacuum apparatus. We'll get everything set and take a look at it. We have raised the target temperature to that of the oven. Otherwise, most sodium molecules would stick at the target. The beam does not stop at the target, although it appears to, but instead scatters in every direction away from the target surface. The density of scattered molecules is so small that we can no longer make them visible on the film. However, we can reach one very important conclusion. The beam is not scattered from the surface as if it were a light ray reflecting from a mirror. Otherwise, we would see the reflected beam clearly. In general, nearly diffuse scattering is typical for gases at ordinary or even highly polished surfaces. However, highly directed scattering is sometimes observed, particularly when the surface is clean and composed of atoms in a well-ordered crystalline array. Here, we can show how the outgoing molecular momentum is related to the incoming momentum and to the target temperature. We use a beam of air molecules in free molecular flow. This is our evacuated chamber. The principle is much the same as with our molecular beam apparatus. Here is a plan view of our experiment. We have a source aperture, a knife edge, and a target. Molecules emerging from the source aperture strike the target and transfer momentum to it. The knife edge screens half the target from the molecular stream. Everything is enclosed in a glass envelope and is under vacuum. Here is the source aperture, the knife edge, and the target. The target is suspended by a torsion wire. We will see the angular position by light reflected from this little mirror. Here is the spot. I'll mark the starting position. And now I'll turn on the flow. And here is a deflection. I'll bring the target back to its original position by twisting the top of this torsion head. And wait for it to settle. Now I increase source pressure . And can read a new torque. The pressure is about double, and the total deflection is about double. A plot of torque versus pressure forms a straight line for very low source pressures. Now, we're going to hold the source pressure constant and change the temperature of the target. We'll heat the target with this lamp. We see a deflection in the same direction, just as though I had increased the source pressure. The deflection couldn't be due to light pressure, since I have illuminated the back side of the target surface. What is happening? Part of the torque is directly due to the momentum flux of the incoming molecules, and this remains constant. The remainder is due to the recoil momentum of the outgoing molecules. This part depends on the target temperature and on the degree to which the velocities of the outgoing molecules are representative of that temperature. Here is a collection of results of tests similar to those you have just seen, but with beams of various gases striking the aluminum target. The source pressure has been held constant throughout. Our results for nitrogen lie here. Calculations show that the torques for molecules which have been re-emitted in equilibrium at the target temperature, that is, perfectly accommodated, should lie here, along this line. But neither helium nor neon lie along that curve, although nitrogen does. Thus, we don't observe complete normal momentum accommodation in some cases.
We use this bigger wind tunnel for quantitative studies of rarefied gas flows. Right now we're going to take a closer look at the bow shock wave in front of a model which is in continuum supersonic flow. While we're at it, we'll learn something about heat transfer to bodies in rarefied flow. The model is a flat bar of aluminum. It's mounted on a thin-walled stainless steel tube to reduce heat conduction between the model and the wind tunnel shell. We use a freely expanding jet again. Here is the nozzle, which is large enough to be in continuum flow. The tunnel is pumped down. In order to see the flow in this tunnel, we use the electron gun to fire an intense beam of electrons across the flow to excite a fluorescence in the air remaining in the tunnel. Now I start the flow and bring the stagnation pressure up to 20 millimeters. You see the barrel shock system of the free jet and the bow shock caused by the model. At the position of the model, the Mach number is about 8. The mean free path just in front of the shock is about half a millimeter. Now I'll increase the mean free path by reducing the stagnation pressure. As we saw in the little tunnel, the shock waves become more diffuse as the mean free path increases. Let's see if we can make this result quantitative. We shall probe the inside of the shock wave with this tiny wire here. This half of the wire is iron, and this is constantan. So we have a thermocouple junction in the middle. The wire is small enough to be in free molecule flow whenever we place it in one of the shock waves we've just seen. It's also small enough so that it doesn't disturb the shock wave by its presence. The wire is installed in the tunnel so that it is parallel to the model. We shall move it along the stagnation streamline here while measuring its displacement with the electromagnetic transducer here. Thus we can get a trace of wire temperature versus distance from the model surface on this recorder. The cold junction of the thermocouple circuit is a second wire identical to our probe, stretched across the plenum chamber in here. Thus we record the excess of wire temperature over stagnation temperature. To help us interpret the results, this curve, which is calculated from kinetic theory, shows how the wire temperature changes with Mach number in free molecule flow. The striking result is that the wire temperature turns out to be higher than the stagnation temperature by a ratio which approaches 7/6 for very high Mach numbers. Therefore, as the wire goes downstream through the shock wave, moving from supersonic to subsonic flow, its temperature should fall. The tunnel is evacuated, but there's no flow, so the wire and its cold junction will be at the same temperature. I turn on the flow and set the stagnation pressure to 20 millimeters. With the wire well upstream of the bow shock, where the local Mach number is about 8, it heats up finally to about 51 degrees above the stagnation temperature. The theoretical excess for a wire under these conditions is 1/6 of the stagnation temperature, which is about 300 degrees Kelvin. Let's start the wire moving. You are seeing this in time-lapse photography. The real motion is very slow to avoid errors due to thermal inertia of the wire. The steep part of the trace is the shock profile. The gently sloping downstream tail comes from the gradual subsonic deceleration between the shock wave and the model. Now I'll cut the stagnation pressure in half to 10 millimeters. This doesn't change the Mach number, but doubles the mean free path. If you look very closely, you should see the shock get fuzzier. Let's take another trace at this lower pressure and see what happens to the shock profile. Here are the experimental shockwave profiles. The second is clearly not so steep as the first. To define the thickness of the shock profile, we use its upstream and downstream asymptotes and its steepest tangent. Here they are for the first trace. The distance between these two intersections we'll call the shock wave thickness, delta. We can do the same for the second trace, and we see that the shock thickness is very nearly inversely proportional to the pressure. Here is a table which includes the mean free path just upstream of the shock. It is also inversely proportional to the pressure. Thus, the shock thickness turns out to be proportional to and of the same order of magnitude as the mean free path. This result has been confirmed in many different laboratories by a wide variety of experimental techniques. Before we leave our data, let's notice one more thing. When the wire is in the undisturbed flow upstream of the shock wave, it is much hotter than the model, the temperature of which is shown when the wire touches it here. The only essential difference is that the wire Knudsen number is about 20, while the model Knudsen number is about 0.03. This decrease in equilibrium temperature with decreasing Knudsen number is directly connected with the collisions between backscattered molecules and those of the stream and accompanies the formation of a shock wave.
We have seen that in rarefied gas dynamics, familiar features of continuum flow disappear as the Knudsen number increases. These are replaced eventually by the distinctive features of free molecule flow. In this extreme, the nature of collisions between gas molecules becomes unimportant, and the nature of molecular scattering at a solid wall becomes dominant.